Okay, this is the first Q&A session on Friday of the Maple 2021 conference. I see attendees are still streaming in, so I'll wait a minute or two before we really start. Let me start by welcoming everybody to this session. And good morning or good afternoon or good evening or good night, whatever it is in the time zone that you're in. And I hope you're excited for the talks we will see this morning or afternoon or night or evening, as excited as I am. So I still see a few people more joining us. I'll give it another minute or so, and then I think we'll get started with the first talk.
Hi, can you hear me? Can I start?
All right, so yeah, it looks like we have the people we're going to have for now, so let's get started. The first talk will be by Luis Cabral about symbolic computation of dual metrics associated with Stackel-Killing tensors on curved spaces. Go ahead.
Hello, everyone. I'm Luis Cabral. I'm talking about symbolic computation of dual metrics and their application. This is a work in collaboration with Valerie, and we are from the Federal University of Tocantins in Brazil. In this structure, you have a synthetic structure of the terms that we are going to consider in this presentation, going from Killing tensors, symbolic computation, and graphics associated with these calculations. Okay. In order to start with some basic information, I consider the isometries in curved space. In this equation, we have the usual formulation by means of linear derivative from equation number 1. But in case of non-degenerate metrics, we can describe this equation via terms of symmetrized covariant derivative. The symmetrized covariant derivative given by equation number 2 involves a well-known equation that has the name of Killing vector equation. Yes. Well, with the Killing vector equation, we can have the option to generalize this equation using, instead of vector, in this case vector is xi, we can use another object, a tensor of rank 2, with the same structure. However, this tensor is symmetric tensor. It's a rank 2 symmetric tensor. These are the basic objects to construct dual metrics. Another important object to consider is the evolution on phase space and conserved quantities. The evolution of phase space is very used to consider the Hamiltonian of a particle in curved space. Using this Hamiltonian, it's possible to consider the evolution, temporal evolutions of some quantities in this space by means of Poisson bracket. Okay. Well, by this structure, it's possible to consider conserved quantities. These quantities can be obtained by means of contraction of the momentum with vector or tensor. Performing a Poisson bracket of these quantities, it's possible to see that the result gives a conserved quantities by means the evolution, time evolution is equal to 0. But all this evolution depends on the symmetrized covariant derivative. Well, this symmetrized covariant derivative depends on the curved space, metric curved space. If you have a closer look at the higher rank tensor, in this case a Stackel-Killing tensor, you see that there is, in this case, a geometric duality. What means a geometric duality? You have a metric, Gemini, or a tensor, xi. But the Poisson bracket equals 0 and the commutative, you have on the other side a dual metric Zymini or a Killing tensor Gemini. That's an important fact about geometric duality. If you look at the equation of the Killing tensor, that is in fact a symmetrized equation, it's possible to find the components of Zymini. We have the component that depends for the space variables or another variables. Look at this solution of that equation. It's possible to use for the basic metric Schwarzschild metric, and the components of the solution for the system of partial differential equation is shown here. Yes, the special solution only for Schwarzschild metric. But the problem with the structure is to find the singularity behavior of dual metrics. We can use the Friedemann scalar, but there is a trivial solution for Schwarzschild, only one singularity for the radial coordinate going to 0. Okay, the problem is the Friedemann scalar, that's the full contraction of the Riemann tensor for the dual space-time. There is a lot of terms, and you need to choose some special constants. A particular case is given here. Okay, well, at this moment, we have to construct the dual metric components on Maple in order to see all the operations necessary to compute the curvature terms, and after that, we can compare terms according to the constants. At this moment, you can see the instruction of the Maple worksheet, where you can load the dual metric. Here we have the components of the metric. It's possible to see with more details in Maple. But if you try to consider the full contraction of the Riemann, it's not possible to display. In that case, you can choose some constants. You can see there is no similarity structure with the Schwarzschild invariant. Friedemann scalar invariant from Schwarzschild is very different for the dual metric. However, there is a lot of structure related to that. To see this in a simple terms, it's possible to consider the graphic analyzing the singularity behavior around the radial coordinate. That's a similarity. However, if you consider another choice constants, there is not equivalent singularity behavior. We have a distinct singularity here for the dual metric. Okay. For example, for the Schwarzschild Friedemann scalar, you have a smooth surface, but for the dual metric scalar Friedemann scalar, you have a non-trivial structure. For example, fixed the cosine of theta equals to 0 and varying some constant. Another different structure you have here, however, fixing one kind of constant, but varying the cosine of theta in the interval. Well, we have in this case all the structure in the simple term by means of graphic, but even the graphic is not so simple to comprehend because of the kind of constants involved, but all the symbolic operation that's necessary to perform some calculation. Maple is very useful to perform tensor calculations by means of symbolic computation. And beyond that, performing symbolic computation, it's very important to display the results by means of some scalar quantities. Well, at this moment, that's enough to talk about it is for you. And feel free to ask some question. And thank you very much for your attention.
Thank you very much, Luis. Everybody here is probably familiar with how this works by now, but just in case, if you have any questions, there is a Q&A button at the bottom of your Zoom window, and you can enter your questions there. In the meantime, I had one question for you, Luis.
Okay.
I noticed from the presentation that you used the package GR tensor by Musgrave, Polny, and Lake. I was wondering, just out of interest, have you considered, or do you have experience with also the differential geometry package and the tensor sum package? Because I believe it should offer the same functionality now. It has for a couple of years, and I was just wondering what your experiences were, or if you have any experiences with that.
Yes, I began to use Maple with GR tensor for a long time ago in my undergraduation. But after that appeared the differential geometry package. During this time of presentation, before the presentation, I was trying to compare the calculation with both package, with GR tensor and differential package from Maple. It's very interesting, some operation, but as I have some experience with GR tensor, I prefer to show the calculation with that. But that, in fact, as I was studying, the operation differential package has some similarities, but there is the physics package and differential geometry. Right. However, yeah, I prefer to use the differential geometry because I have a free calculation space. I can reduce it to lower dimension because I'm applying the situation for three-dimensional situation also. But this differential packaging was very useful for me.
Understood. Okay, thank you very much for that answer. We don't currently have any further questions, but if any further questions for Luis arise, we should have a little bit of time at the end of the session, and you can ask those questions later. So with that, we will switch to the second talk of this session, which will be Friedemann Groh's. Luis, if you could stop sharing, that's wonderful. Okay. Thank you. And we'll switch to Friedemann. Friedemann, you can start sharing your screen.
Okay. Can you see it?
Yes, I can. And Friedemann will discuss calculating multiplication matrices via the Schur complement. Go ahead, Friedemann.
Thank you. Thank you. First of all, thank you very much for coming to my presentation on multiplication matrices. The message I want to convey can be best expressed by running a Maple script. Here it is. The whole method works for a particular class of algebraic systems, of which I show a typical example. It is here. This one here. The coefficients are indeterminate and not coupled by constraints. The entire system is described by its exponents here. It's integer exponents. Not surprisingly, this information is sufficient to determine the desired multiplication matrices. This part of the algorithm is not yet implemented in Maple. However, it should, since each step can be performed in exact arithmetic. We run it anyway. Read in the system. Now it calculates, and we see what comes out. Yes, here is a list. And it encodes all critical resultants of the system. If one of them is 0, a solution goes to infinity. Apart from that, the script has generated more tables that can be now read in Maple to produce the desired multiplication matrices. Here it is. Here the output is loaded. And here the multiplication matrices are computed without Grübner basis. We see this happens in this row. And we see here that this operation requires a generalized inverse of a rectangular matrix. There's strong evidence that this operation works precisely when none of the critical resultants vanish. To investigate this, I used the theory of sparse polynomials introduced by Sturmfeld, Emiris, D'Andrea, Sombra, and many others. Here below, the zero of an example is calculated numerically via eigenvalues. I checked the errors. They looks reasonable, and it shows again the purpose of multiplication matrices. The purpose is to solve such algebraic systems as shown here for certain coefficients. Finally, I show an analysis of singularities. So I switch back to Octave in this case, and once again I read in the system.
Friedemann, we can currently only see your Maple session. I think you're showing something else, right?
Yeah. So you see, don't you see? Okay.
Yeah, there's a selection in the. If you go to the top of your screen, where there is a bar, you can select share your whole screen. I forget how exactly.
Okay. Share the whole screen. Sorry. So, this is the other script I wanted to show, and I wanted to point out that the Who algorithm calculates this critical resultants. If one of them goes to 0, a solution is it diverges. And here I show an analysis. One of the critical resultants is smaller and smaller, and 2 components of one solution goes to infinity, as shown in this double logarithmic plot. And I choose this resultant here, this one, and this analysis is just a demonstration how the whole theory works. And again, it is encoded in this line here, in this line, and this direction vector here shows which component of the solution diverges, and it's here it's the last 2. These remain bounded, limited. Only these diverge, and it's shown in this diagram here. These 2 goes to infinity, and these are small. Yeah, that's my presentation, and I wanted to demonstrate how multiplication matrices can be calculated completely without Gröbner basis and any term order. To me, it's a very nice application of the theory of sparse polynomials, Newton polytopes, and so on. Yeah, so now I look forward for any questions. Hello?
Thank you very much, Friedemann. So once again, if any of the audience members have any questions, please enter them into the Q&A window. In the meantime, I wanted to also ask one question. So I looked, of course, at your longer presentation.
Thank you.
Through the theater, and I was wondering. So the way you describe it in the longer presentation, you describe it as working with an external C library. So the external C library is that basically the Octave script that you're showing here?
Yes. Okay. Yes, it is. So what I wanted to in my presentation, I wanted to I mentioned application which is not implemented yet, and the idea is to calculate to split up the problem. First of all, here, all calculations, all exact calculations should be done in Maple. Then Maple generates a C script, and this C script can be used to, this C script just reads in these lists, previously compiled lists. Then it can generate multiplication matrices for specific coefficients. These coefficients are input of this function, which should be generated, and then I can solve it here using standard numerical algorithms, and so I can And so that's a suggestion here to use Maple as a kind of compiler. In the high-level language is the algebraic system, and the analogon to the machine code is the C code. It should then produce. And in this case, smaller companies like the company I work for can use these scripts and can solve smaller or more complicated algebraic systems in a structured way. That's what I want. That's a suggestion behind.
Wonderful. Thank you very much. In the meantime, we received one question via the chat. Luis Cabral asks, do you have the option to use MATLAB and Maple? So I guess the fact that you're using Octave,
no, I have, but here not in my. I can use Maple, but it's here. It's another on this laptop. I use Octave, but on my regular I use Maple. Yeah, I have the option to use all of that.
Right. Wonderful. Yeah. All right. Thank you very much for that explanation and for the wonderful talk. And then we're moving on to the third talk, which is Jean-François Hermant. Friedemann, could you stop screen sharing? Thank you. That's wonderful. And then Jean-François, you could start sharing your screen. And Jean-François will be talking about teaching elliptic curve cryptography. Very excited to see what he will say about that. Okay, Jean-François, we're ready to go. Go ahead.
Yes, I'm ready. Can you see my screen?
Yes, we can.
Okay, sorry, because I have a very bad internet connection, so I will try to do my best. So the presentation is how to use Maple to learn elliptic curve cryptography. So in this presentation, we consider one of the fastest ECC curves, namely curve 25519. It's a curve that was first introduced by Daniel J. Bernstein in 2005, and it is now used in many applications. So here we have the equation of the curve: y squared equal to x cubed plus 486662 x squared plus x modulo p. So it's a Montgomery curve over the prime field defined by the prime number 2 to the power 255 minus 19, and it uses a base point x equal to 9. So we use Maple to write, we were asked to write a program in cryptography for a cybersecurity challenge and to solve it. So I will explain how we write the program and how to solve it. So an elliptic curve is given in the program statement with one of its points. So it's not the equation of this curve. This coefficient is hidden, and we use another point than the base point. So the first step of the challenge is to recognize the ECC curve used. So there is a smart, straightforward method to recognize this curve. And once we have this curve, we compute 2 points on this curve. The first point is P1 with these coordinates. Second point is P2 with these coordinates. And in the program statement, we only give the ordinates y1 and y2. So the second step of the challenge is compute x1 and x2 given y1 and y2. And of course, this x1 and x2 may or may not be unique. And the first step of the challenge is to use the Chinese remainder theorem with these points, P1 and P2, to decipher a PDF file. So here you have the cybersecurity challenge. It's called the elliptic VX, so it's the name of the challenge, Brigitte Friand. So here you can see the equation of the curve, y squared equal to x cubed plus a. So you don't have the coefficient, you just have a. X squared plus x modulo n. You have the value of n, 2 to the power 255 minus 19. And we give this point, a point of the curve, which is different from the base point, x equal to 9. So we have this point, P. And we also give two other points, K1P with these coordinates, x1 and y1, and K2P with these coordinates, x2 and y2. And we give in the challenge only y1 and y2. And what we want to do is to solve, to compute the value for x1 and x2. And once we get this value, x1 and x2, the key to decipher the PDF file is defined by this equation. So we use the Chinese remainder theorem to solve this equation. And we get this solution. I will try to present another. Okay, this one. Where is it? Okay, can you see the other screen?
No, we don't. Oh yes, now we do.
Okay. So it's the mapper sheet. So we have the base point. So it's given in the RFCs, or we can also compute it with Maple. We just have to solve this equation modulo P, and so you know x1, x0. Sorry, it's 9. You need to find y0. So you know the modulo. And so you are also able to compute this value for y0. So this is the base point for the curve. To compute the point P1 and P2, we have this procedure, the point doubling. You have a point P and you compute P plus P. So you have 2P and you keep iterating and you compute this point P1. It's 2 to the power 1922 P0. So you keep iterating and you find these values for this point, P1 on the curve, okay? The other point, P2, you keep iterating to 2013 and you will get this value for X2 and Y2. So again, you can check that this point is on the curve, P1. In the problem statement, we don't use P1, it's the point negation of P1. So I will explain later. And P2, so we can see that these 2 points, P1, P2, are 2 points on the curve. And then in our challenge, so we hide this coefficient for X2, BA, and we give the point P as P1. So the first thing to do is to recognize the curve. So if you notice that n, it's a well-known modulo. So if you see that n is equal to the power 255 minus 19, so the thing to check is if it is curve 25519. So we check with the point P1 that this point belongs to this curve. So it's a straightforward way to find the curve. Otherwise, we can use the msolve command or to compute a modulo n to see that it's this curve. And once we get this curve, I said that we use the point negation of P1. So instead of using y1, we use minus y1 modulo P. So this is a way, if we see this, we don't even need to compute x1. X1 is one of the 3 solutions of this equation. Okay, if I remember correctly, it's the last one. And for the other point, we have to solve this equation and we can find point P2. And once we get this solution, x1, so you know for x1 there are 3 possible solutions. We can compute the Chinese, apply the Chinese remainder theorem to compute z. It's I don't remember where it is. It's defined somewhere. Okay, it's not here, but it's the Maple command here, Chinese remainder for x1, x2, modulo p and p minus 1 divided by 2. So we are able to compute 3 keys. And of course, there is only one key that is the solution to solve, to decipher the file. Okay. Do you have any questions?
I don't. Oh, that's Luis, is that right? No, who is that? That's Friedemann. Go ahead, Friedemann.
No, that's not me. Sorry.
Oh, sorry. Who was the question from?
Hi, I have a question.
Please go ahead, Luis.
Hi, it was a very interesting subject. I have a question about the time involved to perform the computation according to the size of the PDF file.
Yes, I think it's so you know you have this base point P0. We compute P1, P2. So to compute the point, it takes something like 30 seconds. It's it's 2 to the power 1972 for the first point, 2 to the power 2014 for the second point, but you compute p plus p, so it gives you 2p, 2p plus 2p, and so on. So you see, it's quite, you can compute these values in approximately 30 seconds, if I remember correctly. And then once you have these points, in the problem statement, you give only the ordinates. And so it's almost immediate to compute the x. The trick in the problem, it's not to compute k1 and k2. It's to solve the equation y squared equal to x cubed plus a x2 plus x modulo p or n. And so you know the value for y, you need to compute x, and this is almost immediate with Maple. And once you get the value for x1 and x2, applying the Chinese remainder theorem is it's the same. It's almost immediate to find the solution.
Right. Thank you for that explanation. If there are more questions for Jean-François or Luis or Friedemann, we can look at those after Valerie's presentation, which will be next.
Okay.
All right. Hello, and thank you for coming to see these presentations today. I'm going to be just doing a summary of my presentation, which was on easy tools for visualizations in Maple. One of the first things I'll take a look at is one of the easiest ways you can get a plot in Maple which is by using the plot builder. If you define a function, or in this case, 2 functions for a parametric plot, you can go over here to the right-hand side where it says plot builder. If you click this button, it will actually open up the plot builder to use in Maple. And we can choose which type of plot we want to do. We could do a 2D plot or a 2D polar parametric plot. If you click the wrong one, you can easily go to this drop-down menu and select the one you would like to use. You have lots of options available here on this right-hand side to change how your plot looks, including this switch here, which will allow you to see the actual Maple command for the plot as well. You can change the color easily as well. Decide if the plot would be filled or not. Change the axis coordinates easily. And you have various other options as well, such as axis, title text, legend, captions. You can change the color options, the color palette as well, and various other options here as well. For typing, once you type in your title, you get options such as changing the font and the font size, and you get lots of various options here that you'll see once you've edited things update. And it's a great way for creating a basic plot and then having the Maple code if you want to keep this plot for later use as well. And just like that, you can keep the same plot to add anywhere else you'd like to use it as well. The next thing we'll look at is the explore command. At its base level, the explore command essentially allows you to explore through math in Maple. So something like this, you can just see the different values of the summation. But what's more interesting with the explore command is if you put a plot function with values that aren't determined by the plot function itself in the explore command as well, and then hit explore in the context panel on the right-hand side. We'll click to skip t in this case because t is part of the plotting variable. So we can now actually explore through this plot. And we can see how the plot changes as you change the slider. Explore can also be done using a command. So in this case, we have the explore command, which you can see here. And using the command itself, we can create an interactive app to view something. Just a simple example in this case, but you can create a lot more examples very easily, very quickly, just by using the explore command to create easy, quick visualizations. Similarly, you can do math apps in Maple. Math apps allow you to go a little bit more in depth than the explore command, but they also take a tiny bit more effort. So what you can see here is in this math app, there's 3 lines of code that really matter to change how this math app works. And the 2 key components to building any math apps are document tools get property and document tools set property. The get property command will get the property of one interactive component, whereas the set property command will then set something to a different component. In this case, we have a plot that's saved to the variable myPlot, which can then be set to this document component here, which is a plot component. The document components can be found on the left-hand side in the palettes. There's many options here available. And when you want the document to be interactive, you can right-click on the component you want to have the code run in. You can click Edit Value Change Code. And as you can see here, those 3 lines that I had in the code edit region live inside this button. And by doing that, whenever I change the button, these 3 lines of code will run and update the math app. You can also do this by putting these inside a procedure and putting these inside the startup code. And that's a common way of doing this as well. It's often much cleaner in the end, but just to keep in mind, these can be as simple as just 3 lines of code as well. Another great thing you can do with Maple is have a combination of Maple and Maple Calculator visualizations. If you have a visual in Maple and you want your students to be able to see this visualization in the palm of their hand, they can actually open up the Maple Calculator, take a picture of any math from their math notes or from the whiteboard, and then they'll be able to actually see the same plot that you would be displaying on the blackboard in the palm of their hands, allowing them to interactively rotate the plot, see it from all angles, and better understand and get an idea for what the plot actually is by actually having that full control and full interactivity as they're learning from the lecture as well. Another great place for interactive documents is Maple Learn. So here's a great example. It's a simplified version of one of our example documents for the regression command. So you can see here, you have this table of values and you can perform a regression on it and see the plot of it. But you can also change these points that are inside the table and see the regression for this completely new example as you change these around, just to get an idea of how the regression actually works, and using visualizations and interactivity to learn or in some cases teach, and better understand what's actually happening when you're learning a new subject. I went through that very quickly, but if anyone has any questions, I'd be very happy to answer as well.
Thank you very much, Valerie. So that last example in Maple Learn, I wanted to ask, so I saw you had, and basically, how do you make that link between that table of points and the points on the canvas there?
Well, one thing that's great about Maple Learn is a lot of these things are automatic. So if you go in Maple Learn and click tables, you can insert a table. It'll start with just one row, one column. We can add a column to it to create those X and Y values. And we can just add any points within. I can go between these points using tab here. And you see it'll just put these random points. And as I click and drag, it'll automatically actually update between the table and the plot on the right-hand side here as well.
That's wonderful. Nice. Thank you. There's one question by one of the attendees, Scott Gold. Scott asks, if I were to teach myself how to write good programs using document tools, what manual or what help pages or what other documentation resources would you recommend?
There is actually, if you go to, there is an overview within our help page of the document tools as well, and they kind of give you an idea of what each of the commands do. In this case, we'd actually want to look at the components, but we can see what each of the components do. And like I said, most of the time, everything you want to do is using that set property and get property commands. And you would look at these individual components themselves to determine which properties you want to set. So you can have any of these components as well. You can see on the right-hand side there. As you drag them in, they have these different properties available. You can also see them by right-clicking and doing component properties. And most of these properties are settable or gettable by the set property or get properties command. As well, I believe there was a Maple Primes post at some point that kind of went through step-by-step how to create a math app. And as once in a while, we as well will do webinars or presentations on how to create nice math apps in Maple as well. Any of those might be a good resource for learning, I think.
One more that I would add is there is a chapter of the Advanced Programming Guide called, which is number 13, chapter 13, which goes into some detail for this. So that would be another option, Scott. A second question from Luis Cabral, who asks about the graphics from the Maple calculator. So how can that be used in the same setting as Maple, or the same setting as Maple Learn? How does that work?
So the graphics from the Maple calculator, these are all on your phone. So anyone with a Android or iPhone can download the calculator from the store. And this is unfortunately just a video, so I can't demo it as well. But if you have the app open, basically any math you input using the edit or taking a picture of, you can then display. It's not directly connected to Maple in the sense that you have a Maple thing open in a worksheet and then it'll open in your calculator, but you can take a picture of the math with the calculator and upload it to the Maple cloud. And once it's uploaded to the Maple cloud, it can either be brought into Maple or brought into Maple Learn as well. And that's how they can connect.
And I think the connection to Maple Learn is currently particularly easy, right? You can basically immediately open that straight away.
I don't have any good examples present, but you can see these are the last things I've taken pictures of. in MapleLearn with the connected account right now. So these are something I took a picture of, and then you can just bring it into MapleLearn from these cloud expressions.
Great, thank you.
All right.
Okay, there's one more question that I wanted to ask of Jean-François. Jean-François, so I think I understand most of what you were showing. What I didn't show is how you knew, or was that maybe just a guess, to know that you could find P1 and P2 from just doubling P0 a couple times. Was that a lucky guess, or was there something about the y coordinates that would lead you to assume that? You're currently muted. I don't know if you're trying to answer. Okay, maybe I'll ask that question separately. If there are any further questions, by the way, for any of the 4 speakers of this session, then now would be a good time to ask them. And if there are no further questions, then I think so. We have another 2 or 3 minutes left in the session, in theory. Maybe I'll say a few words about what's next in the conference. So let me find the program. Where did my program go? So I know there are two more Q&A sessions in parallel, and I was going to find what those are. Should be able to find that here. Okay. As my page is loading. Yes, so we have one more Maple in mathematics and one algorithms and software. That will be, so track 1 will be Maple in mathematics, and we talks about the complexity of calculation for adaptive splines, an algorithm for constructing Hermant interpolation, polynomials on a triangle and a tetrahedron, an algorithm to derive a rational function with particular properties, and visualizing intersection curves. And the parallel session will be on algorithms and software. That's track 2, speaking about discussing speeding up polynomial GCD operations, computing a difference equation, and a generics-based expression simplifier. So whichever of those are interesting to you, I would recommend that you attend the corresponding session. And that brings us to the end of this session, and I hope to see you in one of the other ones. Thank you very much, and thank you to all 4 speakers, and thank you to all attendees. Have a good rest of your day.